This block diagram shows a digital to analog converter with 4 digital inputs that pass through a resistor network. A summing amplifier alters the voltage output that can vary from 0 to 3 volts at increments of 0.2 volts. Consider the possible binary inputs at D, C, B, and A, and the corresponding voltage output based on the following truth table. Keep in mind that the inputs going from A to D have increasing significance. The resistor network will account for these input differences by using a specific arrangement of resistors to modify the digital signal. The summing amplifier receives the output voltage from the resistor network and amplifies it to the expected voltages. With an input of 0, 0, 0, 0, according to the truth table, the voltage output would be 0. Inputting 0001 will result in an output of 0.2 volts. If 4-bit value 0010 arrives at the input, the voltage output is 0.4 volts. With each subsequent increase in the binary value, the voltage increments by 0.2 volts. The voltage reaches 3 volts when the binary input is 1111. Let's look at a more detailed circuit of a digital to analog converter to demonstrate how to calculate the voltage output of the analog signal based on the values of the various inputs. The resistor network is made up of 4 resistors with values of 18.7, 37.5, 75, and 150 kiloohms. The summing amplifier has an operational amplifier, or op-amp, coupled with a 10 kiloohm feedback resistor. The feedback resistor's role is to control the voltage gain of the amplifier. With all switches in the 0 position, the input and output voltages will be 0. However, when switch A receives a logical input of 1, it toggles to the closed position. This results in an input voltage to the op-amp of 3 volts. The process of determining the magnitude of the analog output signal from the voltage input of the resistor network requires calculating the gain supplied by the amplifier. Gain can be calculated by dividing the resistance at the feedback resistor by the input resistance. With this 4-resistor arrangement, input resistance will vary in switches A, B, C, and D based on the kiloohm value. Let's look at what happens when switch A is set to logic position 1 or closed. This results in an input resistance to the amplifier of 150 kiloohms. Inserting the values into the equation, the gain equals 10 kiloohms divided by 150 kiloohms, or 0.066. Now the output voltage can be calculated by multiplying the gain by the input voltage of 3 volts. Thus, the product of the amplifier gain of 0.066 and 3 volts is 0.2 volts. Thus, a binary input of 0001 yields an output of 0.2 volts in accordance with the truth table described previously. Applying a binary of 0010 will move switch B to logic position 1, resulting in an input of 75 kiloohms. Plugging these numbers in the equation gives a gain of 0.1333, resulting in an output of 0.4 volts when the input voltage is multiplied by the gain. Again, this result conforms to what is expected based on the truth table. Let's switch in another resistor value and look at what the voltage output would be. A binary input of 1000 closes switch D, resulting in an input of 18.7 kiloohms. The gain then would be 0.535, giving a final output of 1.6 volts. As previously mentioned, observe how the voltage increments by 0.2 as we open and close the various switches based on binary inputs. Finally, we can generate an output of 3 volts by inputting binary code 1111.